last time we looked at conjugate gradient method, we saw that it blew steepest descent out of the water, right? And so today's class is to show you that all is not that hunky-dory. There are places where it runs into trouble, okay? So let's start. So I'm going to draw an approximate graph, okay? So let's say that we are very happy with our CG method and we want to study how does it behave with condition number. We know that it's going to get worse as the condition number increases, but how worse, right? So there is a MATLAB code on the website that, I mean, which we discussed last time. You can manually play around with the condition number and make your problem easier or hard, okay? And then you can plot this graph, which shows you that as the iterations go, how close do I get to the solution, right? So what you will find is something like this. This is, let's say, kappa 1, okay, and then you will have kappa 2, and then you have kappa 3, okay. So kappa 1 is something like this. We don't need the exact details, but the condition, the behavior of the error is something like this, okay, and this is actually in log. So what are the few observations that you make from here? For example, if I were interested in a certain threshold to stop my iterations, okay, or certain accuracy, that would be a horizontal line in the graph or a vertical line in the graph? Horizontal, right? So let us say that I want to get, as long as I get an error below this threshold tau, I'm happy with my solution, right? It can happen. I don't want 10 to the minus 16 error, I want 10 to the minus 4 is good enough for me, okay. So this tau could be, for example, 10 to the minus 4. Now what is our very obvious observation? To get the same error, I need more iterations if the condition number is worse, right? So we can say for the same error, higher, oh, this is slightly confusing over here. This should be kappa, okay, this is kappa, not k. For higher condition number implies more iterations. That's obvious. And if I had fixed computational resources, if I wanted to devote only so many iterations to this problem, that would be a vertical line on this graph. So something like this. That's my vertical line. So what is our observation looking at this vertical line? That if I have a fixed number of iterations, the one with a higher condition number has higher error, right? So for a fixed number of iterations, higher kappa, which is condition number, implies higher error, let's say more error. Those are the two very basic observations that I can make by looking at this graph, right? So obviously people looked at this and said, hey, is there a way to improve this, okay? So that's what leads to this idea of preconditioned conjugate gradient method. So let's see what that means, okay? So we are going to stay within the arena of conjugate gradient method, which means that I am constrained, means I have my CG routine, I am constrained to use it. Therefore, what is the limitation on A? What can I not sacrifice about A? Symmetric positive definite. Only then I can use the CG method that I have studied, right? So I am going to keep as fixed A must be symmetric positive definite. Okay. Remember, for CG, what was I trying to solve? Ax is equal to b, and we wrote that neatly as a objective function, as a quadratic form. Now let's stare at this a little bit. A has a bad condition number. I still want to use the CG routine in solving this. What could I possibly do? Multiply with the other matrix, okay? Then what will happen?
We can alter the eigenvalues.
Okay, so that's a good idea. So supposing I multiply this with some matrix, let us say T. Multiply on both sides by T. So T tax is equal to TB. Okay. The motivation being that T into A may have a better condition number than simply A. Okay. So kappa of TA less than kappa of A. Is that a good idea? The answer is literally staring at you in the face. Is that a good idea? No. Okay, I am seeing some head shaking. Why not? I mean, if condition number is less, then that's great, right? Why is it a bad idea? Huh? The matrix, I cannot input this into my algorithm unless I make sure that T into A is also positive definite. That is not guaranteed, right? So T into A may not be symmetric positive definite. But this motivation which you had over here, this idea, this is the essential idea. This is the only knob we have in our hand. If we can somehow make the condition number better, then there is some hope. So this looks like a small roadblock along the way. Now let's pretend for a minute that symmetric positive definite, let's relax. Just pretend for a minute. Let's live in the ideal world. In the ideal world, it will sound very impractical, which is why you may have a difficult time guessing it. What is the ideal T? A inverse. Right? What is the best condition? In another word, what is the best condition number I can get? 1. 1 is possible only if T is A inverse, right? So in the ideal la la land, T is equal to A inverse. And in this ideal world, this is ridiculous because if I already knew A inverse, there is no problem left, right? So this does not work. However, that gives us an idea of what we could do. Okay. So the trick that I am going to do is, I want to achieve two things: a reduction of condition number while maintaining positive definiteness. Okay. So supposing I take my Ax is equal to b, and like was suggested, let's multiply by some matrix. Okay. Instead of saying T, I am going to create a new convention. I am going to multiply by, say, a new matrix L transpose Ax is equal to L transpose B. Okay. So I am doing a right multiply by some new matrix. L transpose could be my T. Okay. I am still in the same problem as before, that I do not know whether it is positive definite or not. But is there a clever trick I could do? N is, assume L is your favorite invertible matrix. Is there some small trick that we could do to shift this into, or transform this into another problem where I have the symmetric positive definite? Okay, so let me give you a hint. Can I do something over here? And it's related, the hint is related to the question that was just asked. What property of L was asked? Is L invertible? So what can I possibly insert here? LL inverse. So let's try that, right? So I'm going to get L transpose, oh not LA, L transpose A LL inverse X is equal to L transpose B, right? So far no cheating, I just need L should be invertible. Okay. Now what? Is it looking closer to what I wanted? I need to group some terms in a nice way. Okay, so if I group like this and like this, okay, so I am going to get, let's call this A hat, okay, let's call this X hat, alright, and yeah, let's call this B hat. So I get A hat X hat is equal to B hat. Now, is A hat symmetric, positive, definite? To check positive definite, what do I need to do? I need to quickly do Z transpose A hat Z should be greater than 0 for all Z not equal to 0. Is that the case? It is, right, because you can immediately see this will be Z transpose L transpose A L Z, and I can combine this. This is already greater than 0, right? So this is symmetric positive definite, perfect, right? And I don't care what B hat is, it's whatever, it's some new vector B hat, okay. So I have kind of shifted the problem. I have not solved the problem, I have just kicked the football a little bit further down. What have I kicked it into? Now what is the new problem that I have to find? Give me a good L, otherwise, right, how do I do this? Okay, so let's see what we can do. So let's assume, so let's defer the choice of how to come up with L, okay, but we have got a way. We have got a way by which I can improve the condition number of this A hat and solve the problem. Once I solve X hat, how do I get back my X? Multiply by L, right. So once I get, so X, L inverse X is equal to X hat. So if I could solve this problem, I just need to multiply by L and get back my X, I am done, okay. Now the part of how to get L we will get to, as I mentioned. A very what should I say, important question is, do I need to rederive the entire, I could solve, supposing I gave you a L, you could take this guy and feed it into a CGE routine and get the solution, right. The trouble is that I have to rewrite my code. Now the question the little more clever thing to do is, you already have a piece of code written for the CG method where the inputs were A and B, right, that is what I had, and later I discovered that the condition number was bad. Now I am asking, can I be a little bit more clever so that I can use that code as much as possible without having to recreate all the variables in terms of the hatted quantities, okay. So you will find a very surprising answer that there are actually very few modifications that you need to do in order to make this work. So we will work that out. Having worked that out, we will see a very clever choice for L that will come up. There are lots of, it's a field in itself. So this L, for example, is what is called a preconditioner, because it's conditioning, preconditioner, right, it's changing the condition number. There are lots of methods, we will talk about one possible way of doing it. But has everyone got the motivation over here? We did some very simple linear algebra tricks to make sure it's symmetric positive definite, that's all.